We are going to look at the cyclic group Z sub 10, which is the integers from 0 through 9, closed under addition mod 10. We're going to look for patterns in the orders of the elements of this group and generalize those patterns to any cyclic group that has the same order. So we'll first generate this group with 1, begin with the identity 0, and add 1 until we get all the way around. Because 1 is a generator of this group, we know that it has order 10. However, it's not the only generator. We can find the other generators by finding the numbers that are relatively prime to 10. This is 1, 3, 7, and 9. So all of these elements, 1, 3, 7, and 9, have order 10. They are generators. Okay, what about 2, 4, 6, and 8? Well, those elements are not relatively prime to 10. The greatest common divisor is 2. 10 divided by 2 is 5. So the order of the elements 2, 4, 6, and 8 is 5. The order of the identity 0 is 1, and it will always be 1. And then we have the element 5, which also is not relatively prime to 10. The greatest common divisor of 10 and 5 is 5, and 10 divided by 5 is 2. So the order of the element 5 is 2. So here are all the orders with their color-coded. All right, good. Now, we're going to change the way we say this a little bit, change the way we view this. Instead of saying the order of 1 is 10 and the order of 2 is 5, we're going to say the order of the first element is 10 and the order of the second element is 5. And we'll generalize that. So here are all the orders not based off the element itself, but the placement of the element. So the first, third, seventh, and ninth elements have order 10. The second, fourth, sixth, and eighth elements have order 5. All right, let's see if this holds true. Let's generate the same group again, but with a different generator. We'll count by 3's, mod 10. We get the same elements, but we get them in a different order. But what we'll notice is that the first, third, seventh, and ninth elements, which here are 3, 9, 1, and 7, are the generators, the ones that have order 10. Whereas the second, fourth, sixth, and eighth elements, which are 6, 2, 8, and 4, all have order 5. The identity is in the same place with the same order, and the fifth element is in the same place with the same order. Good, let's generate using 7. Same group, just in a different order, but again, the pattern doesn't change. I'm going to use the colors now. You notice that the blue numbers are still in the blue number places, and the purple numbers are in the purple number places. The identity is still where it was, and the fifth element is still where it was. Everything has the same order. Same is true if we generate using 9. All right, good. So what we're seeing here is that we can find the generators just based on location. So let's see this in the context of a different group. We'll do U sub 22, which is the group of all the numbers that are relatively prime to 22. There are 10 of these, so the order of the group is 10, and 7 is one of the generators. We begin with 1, which is the identity, because this group is closed under multiplication, mod 22. Multiplying by 7, we get these numbers. All right, good. Well, to find the other generators, you don't have to go through and check every element, right? Let's check all the powers of 5 and see if that generates the group. No, you don't have to do that because 5 is the second term. It's the second element, and we know that the order of the second element is 5, thus it will not be a generator. Okay, so which ones are the generators? Well, the first, the third, the seventh, and the ninth. Which is 7, 13, 17, and 19. And then we know that the second, fourth, sixth, and eighth elements, which are 5, 3, 15, and 9, all have order 5 and are thus not generators. The fifth element, which is 21, has order 2. Neither will it be a generator. And of course the identity has order 1. But anyway, so you can generalize the orders based off their position in the group. And you can use this using the integer group and generalize it for any other cyclic group that has the same order.